You know, we tap on sleek apps and swipe across glossy touchscreens all day long, but right beneath that shiny surface, there's a brilliant, completely invisible manager orchestrating every single microsecond of activity. Welcome to the Explainer. Today, we're demystifying the operating system, the unseen conductor of our entire digital world.
Okay, let's dive right into this outline. First, we'll officially meet this unseen conductor, then look at how OSs adapt for absolutely every device out there. After that, we'll map out the anatomy of a system, peek under the hood, and finally wrap up by meeting the ultimate bodyguard. So, Section 1, meet the unseen conductor, the vital intermediary between you and your raw hardware. At its core, an operating system is really just a program, but it's one that's running continuously in the background. Think of it as the ultimate translator between the raw physical silicon and you. Without it, well, you'd be stuck writing low-level binary code just to get a single letter to pop up on your monitor. Yeah, no thanks. The OS bridges that massive gap so we don't ever have to. To actually pull this off, the OS does this crazy balancing act, which basically boils down to primary and secondary goals. Primarily, it's all about you. It's focused on user convenience and program execution, giving you a smooth interface and making sure your apps have exactly the right environment they need to run. But secondarily, it has to babysit the physical machine. It ensures fair resource management by handing out CPU and memory, pushes for efficient resource utilization to max out performance, and of course, guarantees reliability. So it's making your life super easy on the surface while working in the trenches to make the hardware run as efficiently and safely as possible behind the scenes. Moving right along to Section 2, OS for every device. We're going from massive mainframes all the way down to the phone in your pocket. Now, looking at mainframe operating systems is fascinating because honestly, these are the titans of the digital world. Their evolution actually started way back in the 1940s. By the 1950s, IBM had become a huge supplier, and after some massive feature upgrades in the 1980s, we arrived in the 2000s with incredibly advanced systems like IBM Z/OS. These aren't machines you use to browse the web, right? They're engineered to handle millions of transactions simultaneously with totally fault-tolerant security. Literally, every time you swipe a credit card, a mainframe OS at a global bank is probably managing that data. But obviously, we don't all carry mainframes around in our backpacks, which brings us to personal computing. And think about the stark contrast here. Desktop systems are designed to harness serious processing power, and they draw from a constant external wall power supply. On the flip side, handheld systems, like your smartphone, are built entirely around mobility. Their operating systems have to be incredibly stingy with battery life, operate on way less memory, and flawlessly handle touch-based interfaces. The OS literally has to flip its entire architectural priority list based completely on the physical constraints of the device it's trapped inside. Okay, but what happens when one processor simply isn't enough? Well, you get multi-processor systems. This is where multiple CPUs sit inside a single physical machine, tightly sharing the exact same memory and clock to drastically boost performance. But contrast that with distributed systems. These are loosely coupled. It's a collection of completely independent computers, each with their own memory, all talking over a network. To you, the user, a distributed system looks like one giant supercomputer, but it's actually a bunch of separate machines collaborating. Fun fact, cloud computing platforms, those are massive distributed systems. And here is where the stakes get incredibly high. Your standard general operating system, like Windows or macOS, is all about user convenience. If your web browser takes an extra second to load, it's annoying, sure, but you'll live. But a real-time operating system, or RTOS, that is focused on strict timing accuracy. We're talking about the operating systems running air traffic control, heart pacemakers, missile guidance systems. In a hard real-time system, missing a strict timing deadline doesn't just mean you get a spinning loading wheel, it means a critical, catastrophic failure. The OS absolutely must guarantee predictable, deterministic behavior, no exceptions. Let's zoom in a bit for Section 3, Anatomy of a System, peeling back the layers of a computer. It really helps to think of a computer system as a strict architectural stack. Right at the very top, we have the users. That's us. We interact directly with the layer right below us, the application programs, things like your media players or word processors. But here's the catch. Those apps, they have absolutely no idea how to talk to raw physical silicon chips. And that is exactly where our vital bridge comes in. The operating system sits smack in the middle, catching the requests from your applications and translating them into instructions for the bottom layer, the hardware, which actually executes the physical operations. Now, what's really fascinating is that the operating system itself actually has its own internal layers.
The outermost layer is called the shell. The shell handles user interaction. It basically interprets whatever you click or type. But deep down at the absolute core lies the kernel. The kernel is the true low-level engine of the entire system. It acts as the primary direct interface between the OS and the hardware, dealing with all the really gritty tasks like memory management and device control.
All right, Section 4, Under the Hood. Let's look at how the OS actually helps programs run.
Behind your back, every single second of the day, the OS is providing a whole menu of essential services. It gives you the user interface, it manages program execution, and it handles all your I/O operations, so your keyboard and display actually talk to each other. It also handles file system manipulation, keeping your chaotic folders perfectly organized, but crucially, it handles resource allocation. This is that unseen magic that lets you stream a podcast, keep 20 browser tabs open, and download a massive file all at the exact same time, without the system just completely freezing up. The OS is constantly, flawlessly slicing up CPU time and memory. And hey, if something does go wrong, it's right there handling error detection to keep the whole system stable.
But how does a basic application actually ask the hardware for a favor? Well, it uses what's called a system call. So the crucial point here is that standard programs simply cannot directly access hardware. It's way too dangerous. Instead, the user program formally requests a service, which invokes a system call. At that exact split second, the CPU actively switches from a standard user mode into a highly privileged kernel mode. The operating system safely steps in, performs the requested task, like writing a file to your disk, and then smoothly hands control back to the user program. Which brings us perfectly to Section 5, the ultimate bodyguard, protecting hardware from chaotic programs. This is where the OS drops the helpful assistant act and turns into a very strict bouncer. The number 2 is incredibly important here, because for any of this hardware protection to actually work, the system operates in 2 completely distinct modes, user mode and kernel mode. The hardware literally maintains a physical mode bit just to tell them apart. Why? Because we absolutely have to prevent standard user programs from executing dangerous, privileged instructions. I mean, think about it. If any random app you downloaded could just disable your system's interrupts or directly overwrite memory used by another program, your device would crash constantly. The OS strictly uses these 2 modes to enforce absolute security. This whole concept is usually structured into what we call protection rings. Ring 0 holds the absolute highest privilege, and that is reserved exclusively for the kernel. The outermost ring, which is typically ring 3, has the lowest privilege, and that's exactly where your everyday user programs get to live. To actually enforce this, the OS uses base and limit registers in the CPU to essentially build invisible electronic fences. The base register sets a starting address, and the limit sets the size. If a program in ring 3 tries to reach outside its specifically fenced-in memory limit, the hardware instantly blocks it and traps the error. It guarantees programs only touch what they are strictly allowed to. Which leaves us with one final, truly mind-boggling thought. Just think about the exact device you are using to watch this right now. The screen rendering, the audio perfectly syncing, the network buffering, the memory isolation. How many invisible decisions is your device's OS making per second right now, just to keep you watching this explainer? Millions. Seriously, millions. So the next time you effortlessly tap an app or drag a file across your desktop, maybe take just 1 second to appreciate the incredible unseen conductor orchestrating all that magic under the hood. Thanks so much for joining us on this deep dive explainer. Keep learning, and I'll catch you next time.